Alright, let's take a look at how changing the pH ultimately changes and affects the standard reduction potential diagrams. I'm going to concentrate for this example on the manganese standard potential diagram. For that particular element, we have permanganate, manganese 4 oxide, manganese 2 plus, and neutral manganese as the four main species that you can observe and play with when it comes down to actually handling the chemicals. Each one of these boundaries, of course, represents an individual redox reaction, a reduction to be most exact. And permanganate going to manganese 4 oxide. To balance the reaction, you have 4 oxygens in permanganate, only 2 in manganese 4 oxide, so you add 2 waters. That yields 4 hydrogens on the product side, so you add 4 H pluses on the left side. And with an overall plus 3 charge on the left side and no charge on the right side, that means that you have to have 3 electrons present. For manganese 4 oxide going to manganese 2 plus, you have 2 oxygens in manganese 4 oxide, none in manganese 2 plus, so you have to add 2 waters to the right side, 4 H pluses on the left side. Overall charge here will be 4 plus, overall charge here will be 2 plus, so you need to add 2 electrons to balance the charges. Manganese 2 plus to manganese 0 doesn't have oxygens or hydrogens, so all you need to do is add the electrons to balance the charges. And these are the three equations that we're going to be playing with, and we're going to see how changing the pH affects the overall look of the diagram. The thing to remember is that for the diagram, the standard conditions are such that all the concentrations are 1 molar. And when H plus is 1 molar, the pH is automatically 0. Alright, so let's take a look at something a little bit more realistic, right? Let's see what happens when we change the pH to a value that makes a little bit more sense. But alright, so this is going to be the idea. We are going to change the pH, so we're going to have to look at non-standard conditions, meaning that we're going to use the Nernst equation. And for each one of the changes that's going to happen, we're going to start with this standard cell potential of 1.7 or 1.23 or negative 1.18 for the individual reductions. And now, since the first equation deals with 3 electrons, 0.0592 gets divided by 3. The second one deals with 2 electrons, so we divide that by 2, and the same thing goes for the last equation, which only involves 2 electrons. Now for the log of Q, we have products over reactants, and remember that only aqueous species or gases can appear in the equilibrium equation. So when we look at the first equation, manganese 4 oxide is a solid that will not make it into the equation. Water is a liquid that will not make it into the equation. Permanganate having a charge and H plus having a charge, those things will be soluble in water and will actually make in the equation, but they are both reactants, so they only appear in the denominator of the equilibrium expression. Also, don't forget to include your exponent for hydrogen. For the second equation, same idea, manganese 2 plus with a charge will be soluble, H plus with a charge will be soluble. Make sure to raise it to the 4th power based on its balancing coefficient. And down here, the only thing that has a charge is the manganese 2 plus, so that will be the only thing present. Being a reactant, we only have it present in the denominator. Okay, so these are the expressions, the Nernst equation expressions for each one of the reduction half redox equations. So let's see what happens. So I'm going to clear up the room a little bit just to make it a little bit more simple to see. Let's see what happens at 3 different situations. What happens when the pH is raised to 7, but we keep all of the other concentrations equal to 1 molar? Well, in that case, the permanganate concentration, the manganese 2 plus concentrations will simply equal 1. Alright, and what's going to happen is that for the first event, you're going to have a change in the actual value of E, right? Okay, so I guess I'll get to that right here. So if you input 1 for permanganate, you're going to get a value, but now the pH being 7 means that the hydronium concentration is equal to 10 to the negative 7. So when you put those new values inside the log, take the log of that, multiply by 0.0592 divided by 3, and subtract that from 1.7, the value of the potential will end up being 1.15. On the other hand, let's say that we keep the pH at 0, but we decrease the concentrations of everything else to 10 to the negative 6. That means that the permanganate will be 10 to the negative 6, H will be 1, so the H to the 4th power just goes away. Same thing here, this will be 10 to the negative 6, that will be 10 to the negative 6. What's going to happen for the first reaction is that you will have 1 over 10 to the negative 6, which is the same thing as 10 to the positive 6. Log of that will equal 6. 6 divided by 3 will be 2, so you will multiply 0.0592 by 2, and you'll subtract that from 1.7. So you do decrease it a little bit, but it's not as bad as it was by changing the pH. And then if you do both, decrease the pH, decrease the concentrations of the species to 10 to the negative 6 molar, which are more typical values, in natural water, and raise the pH to 7, then you basically have both effects happening. You decrease the potential with the increase in the pH, and you decrease the potential with a decrease in the concentrations. And that kind of gets felt right here on both accounts. But needless to say, because you have a coefficient of 4 in front of H plus, which means that in your equilibrium expression you have H plus raised to the 4th power, and being the fact that the H pluses are reactants in the equations, you have a decrease in the potential. Alright, now looking at the second reaction, same idea. At pH 7, you have a 10 to the negative 7 molarity for H plus. You have a concentration of 1 molar for the other species, so this gets lowered from 1.23 to 0.40, so it's quite a change, really. And for manganese 4 oxide, on the second step, where the pH is kept at 0, but the concentration of manganese 2 plus is changed to 10 to the negative 6, you actually raise the potential from the original value. And the reason why is because the manganese 2 plus is a product, so raising its or decreasing its concentration ultimately raises the potential because that's a product. And then you have the combined effect right here for when you raise the pH and lower the concentration of everything else. And finally, for the last species, if all you do is change the pH, then the potential doesn't change from the one you have in the original standard table because there is no H plus concentration present in the equilibrium constant of the last reduction. But if you do change the concentration of manganese, now you're going to decrease the value to negative 1.36 because the manganese is once again in the denominator. Alright, so as you can see, the places for the potentials can be drastically changed based on the pH. And it's interesting to see that at neutral pH, you actually stabilize the permanganate as well as the manganese 4 oxide compared to the standard states. And another way to put it is that the oxidative species, the ones that are farther up on the diagrams, are actually less stable at lower pHs than at higher pHs. So if you wanted to deal with permanganate and you wanted to make a solution of it, it's better to make permanganate in basic solution because you will decrease the value of the potential, making it more stable, than if you try to make it in acidic solution, at which point you make permanganate very reactive. Reactive to the point, by the way, that this is high enough to react with water and, just decompose rather quickly. At higher pH, neutral pH, the value is 1.15. It's just barely below the oxidative potential of water, so it's semi-stable. And of course, if you make the pH even higher, you will decrease the value of the permanganate value, so you actually make it stable in water under basic conditions. So by changing the pH, you can, as you can see, for the vast majority of processes, the ones that do have oxygen present in their species, you have the means of stabilizing those species. In some cases, you can make them worse, right? Like manganese 4 oxide, by changing the concentrations, you make the range where it coexists lesser, and so you make it more difficult for manganese 4 oxide to exist under these conditions. But the point being is that you can change those potentials at will, and you have to keep that in mind because if you're not dealing with standard conditions, the values you're getting from the base diagrams may not be fully representative of what's actually going down in solution. All right, so with that being said, I will be testing you on ultimately what happens to the potential, and I might even ask you to sketch those graphs for the reduction potential to see how they get affected upon changing the pH. Um, the most likely scenario that I'm gonna look at will be the one where we keep the concentrations of everything else at 1 molar and pH of 7. But mind you, as of now, everything else is a possibility. I could give you concentrations in the micromolar range for everything else, keep the pH at 0 or change it to 7 or some other value. So just be aware that for the pH, you're going to have to raise 10 to the negative pH to get the hydronium concentration. Alright, so in the next video, I'll talk about something that kind of connects the entire segment of electrochemistry together. They're known as Pouget diagrams. Alright, so see you in the next video.